In just a few weeks, the moon is going to slide perfectly in front of the sun, and for a little over 2 minutes, the sky above Iceland and northern Spain will go dark in the middle of the day. Stars will appear, birds will go quiet, and a pale, ghostly ring of light will explode around the black disk of the moon. The last time mainland Europe witnessed anything like this was back in 1999, 27 years ago. But here is the part almost nobody tells you about total solar eclipses. They are not just beautiful, they are some of the most important scientific events in human history. During these rare minutes of darkness, astronomers have discovered an element that had not yet been found on Earth. They have measured an atmosphere hotter than the surface of the sun. And on one spring morning in 1919, a single eclipse took a little-known physicist named Albert Einstein and turned him into the most famous scientist alive. So before that shadow races across Europe again, let's talk about everything the darkness has taught us. Here's what actually happens during a total solar eclipse. The sun is about 400 times wider than the moon, but it also sits roughly 400 times farther away. That cosmic coincidence means that from down here on the ground, the moon and the sun look almost exactly the same size in the sky. So when they line up perfectly, the moon can cover the sun's blindingly bright surface completely. There is a stunning moment right before that happens, when the last sliver of sunlight blazes through a valley on the moon's edge and flares like a brilliant diamond on a glowing ring. People call it the diamond ring effect, and the instant the sun is fully covered, something hidden appears. A shimmering, pearly white halo of light spreads out around the dark moon, sometimes stretching several times the width of the sun itself. This is the corona, the sun's outer atmosphere, and for most of human history, it was a total mystery. You physically cannot see the corona on a normal day. The light pouring off the sun's surface is millions of times brighter, so it completely drowns the corona out. The only natural way to see it with your own eyes is during the few minutes of a total eclipse. For centuries, people were not even sure what they were looking at. Some astronomers thought the glow belonged to the moon. Others thought it was an optical trick or sunlight bouncing off some atmosphere around our own planet. It took decades of chasing eclipses across the globe, hauling telescopes up mountains and across oceans, to finally prove that this ghostly crown actually belongs to the sun. But proving the corona was real was only the beginning, because once astronomers aimed a new kind of instrument at it, the sun started giving up secrets nobody saw coming. That new instrument was the spectroscope. In simple terms, it splits light into a rainbow of colors, and hidden inside that rainbow are sharp, dark, and bright lines, almost like a barcode. Every chemical element has its own unique barcode, so if you can read those lines, you can figure out what something is made of, even if it is 93 million miles away. On August 18, 1868, a total eclipse swept across India, and a French astronomer named Jules Janssen pointed his spectroscope at the glowing red flames leaping off the edge of the sun. And he spotted a bright yellow line that he simply could not explain. It sat right next to the known lines for sodium, but it was not sodium. It did not match any element known on Earth. Around the same time, an English astronomer named Norman Lockyer caught the exact same mystery line. Working with the chemist Edward Franklin, Lockyer made a bold call. He argued that this line came from a brand new element, one that nobody had ever found on our planet. He named it helium, after Helios, the Greek god of the sun. Think about how wild that actually is. Scientists discovered helium by staring at sunlight. They found an entire element out in space before anyone ever held a sample of it in a lab on Earth. And it took another 27 years, until 1895, before a chemist named William Ramsay finally isolated helium down here on the ground, locked away inside a uranium mineral. The same helium floating in birthday balloons and powering rockets was first discovered in the fire of a solar eclipse, and the eclipses were nowhere near done peeling back the sun's layers. Those glowing red flames Janssen had been studying have a name. They are called solar prominences, and they are absolutely gigantic. We are talking enormous loops and arches of hot gas erupting off the surface and reaching tens of thousands of miles out into space. Some of them are larger than several Earths stacked on top of each other. And sitting just below them is a thin layer of the sun that you can only catch for a heartbeat. When the moon is almost, but not quite, covering the sun, a brilliant strip of pinkish-red light flashes into view right along the edge. That is the chromosphere, a layer of the sun's atmosphere resting just above the visible surface. It only appears for a second or two at the very start and end of totality, which is why astronomers nicknamed it the flash. In 1870, during another total eclipse, an American astronomer named Charles Young managed to capture the spectrum of that flash, recording the chromosphere's barcode of colors in those fleeting seconds. Before eclipses came along, these layers were nearly impossible to study because the brilliant surface of the sun completely overpowered them. But here is where it gets clever. After watching the prominences during that 1868 eclipse, both Janssen and Lockyer worked out a technique to study them even when no eclipse was happening, using the spectroscope to isolate their specific light. All of a sudden, scientists no longer had to wait years and sail around the world just to study the edges of the sun. The eclipse had handed them the key and then shown them how to use it on any clear day. But the corona, that ghostly outer crown, still had a strange structure that nobody could explain. Look closely at a good photograph of the corona during totality, and you will notice it is not just a fuzzy, even glow. It has real shape. Long, pointed streamers stretch out from the sun's middle like flower petals, and near the top and bottom, you can see thin little plumes that look almost like iron filings lining up around a bar magnet. And that comparison is not a coincidence. Those shapes are being sculpted by the sun's magnetic field. The corona is made of plasma, which is superheated gas where the electrons have been torn away from their atoms. Plasma is electrically charged, so it gets pushed, pulled, and funneled along magnetic field lines. The streamers, the loops, the delicate plumes near the poles, they are all tracing out the invisible magnetic architecture of the sun. Astronomers pieced this together by comparing eclipse photographs taken years apart, and they noticed something fascinating. The shape of the corona actually changes over time. The sun runs on a roughly 11-year cycle, swinging from calm to stormy and back again. When the sun is at its most active, the corona looks fuller and spreads out more evenly in every direction. When the sun goes quiet, the corona stretches into those long streamers near the equator and thins out at the poles. So just by photographing the corona during eclipses, scientists could literally watch the sun's magnetic mood swings unfold across decades. But the shape of the corona was only half the story. The bigger shock was its temperature, and the answer made absolutely no sense. Back in the 1800s, while astronomers were studying the corona during eclipses, they kept bumping into another stubborn mystery line, this time a bright green one. It did not match any element anyone had on record. So, exactly like they had done with helium, scientists assumed it must be yet another brand new element. They even gave it a name. They called it coronium. This time, though, they were wrong. There was no coronium. The real answer took decades to crack, and when it finally arrived, it was honestly a little terrifying. By the late 1930s and early 1940s, physicists including Walter Grotrian and Bengt Edlund figured out that the green line was coming from iron. But this was iron stripped of 13 of its electrons. And here is the problem with that. To rip 13 electrons off of an iron atom, you need a staggering amount of energy. You need temperatures of well over 1,000,000 degrees. Now remember, the actual visible surface of the sun, the bright part we see every single day, is only about 5,500 degrees Celsius. Scorching, obviously, but nowhere near 1,000,000. So somehow, the sun's thin outer atmosphere, the corona, is hundreds of times hotter than the surface sitting right below it. It is like standing next to a campfire and discovering that the air high above the flames is somehow far hotter than the fire itself. It completely breaks your intuition. Scientists call this the coronal heating problem, and believe it or not, we still have not fully solved it today. There are strong ideas involving magnetic waves and tiny eruptions called nanoflares, but the complete answer is still out there waiting. And total eclipses are still one of the best chances we get to study it up close. But the single most famous eclipse discovery in history was not about the sun at all. It was about the entire universe. In 1915, Albert Einstein published his general theory of relativity. At that point, he was a respected physicist, but hardly a household name, and his theory made a very strange, very specific prediction. Einstein said that gravity does not work the way Isaac Newton had described it more than 2 centuries earlier. Newton pictured gravity as a force reaching out and pulling on things. Einstein pictured something far stranger. He said that massive objects bend the space around them, and that even a beam of light has to follow those curves. Which led to a bold claim. If starlight passed close to something as massive as the sun's gravity should bend that light and shift the star's apparent position in the sky by a tiny amount. And Einstein put an exact number on it, around 1.75 arcseconds, which is a fantastically small angle. Now here's what made this such a showdown. Newton's older physics also predicted that gravity might bend light a little, but only about half as much as Einstein's number. So an eclipse could act as the referee between Newton and Einstein. There was just one catch. You could never test it on a normal day because the sun is so blindingly bright that you cannot see any stars sitting near it. There is only one situation where the sun goes dark enough to reveal those stars. You already know what it is: a total solar eclipse. So on May 29, 1919, a British astronomer named Arthur Eddington set out to put Einstein to the test. He led an expedition all the way to the island of Principe off the coast of West Africa, while a second team traveled to Sobral in Brazil. As the moon blocked the sun and the daytime sky went dark, they photographed the stars scattered around it, capturing faint points of light on fragile glass plates. Then they compared those star positions to where the very same stars normally sit when the sun is nowhere near them, and the stars had moved by almost exactly the amount Einstein had predicted, and clearly more than Newton's physics allowed. The light from distant stars had been bent by the gravity of the sun. A 200-year-old picture of gravity had just been overturned by a handful of photographs taken in the shadow of the moon. When the results were announced in November of 1919, it was front-page news all around the world. Albert Einstein went from a relatively obscure physicist to a global superstar practically overnight, all because the moon slipped in front of the sun for a few minutes and let us check his math. A 2-minute shadow had confirmed an entirely new understanding of space, time, and gravity itself. So when that shadow sweeps across Iceland and northern Spain on August 12, 2026, and millions of people look up at that pearly white corona hanging in a darkened afternoon sky, remember what you are really seeing. You are looking at the same glow that helped us discover helium, the same atmosphere that turned out to be over 1 million degrees for reasons we are still arguing about, the same darkness that once let us watch starlight bend around the sun and prove Einstein right. And the part I love most about all of this, eclipses still matter to science right now, today. Modern researchers still study the corona during totality to chase down that heating problem. Everyday people with cameras now feed real data into huge citizen science projects, photographing the corona from hundreds of points along the eclipse path to build a complete picture that no single telescope could ever capture on its own. Every eclipse is one more data point, one more chance to catch the sun doing something we did not expect. For about 2 minutes, the most ordinary thing in our sky, the sun we completely take for granted, becomes the single most interesting object in the universe. And the entire story of how we came to understand our own star is written in those brief, breathtaking moments of darkness. The next chapter gets written over Europe in 2026. So if you happen to be anywhere near that path, grab a pair of certified eclipse glasses, find yourself a clear patch of sky, and go witness the same event that rewrote science more than once. And here's what I want to know from you. Have you ever stood in the path of a total solar eclipse and watched the sky go dark in the middle of the day? Tell me down in the comments where you were and what it felt like, because those stories are my favorite ones to read. And if you have never seen one in person, tell me this instead. Out of everything we just covered, the helium hiding in the sun, the corona somehow being hotter than the surface, or the starlight bending to prove Einstein right, which one made your jaw drop the most? Drop your answer below.